Hi, welcome to this new video in which we will see how considering and ignoring axial deformations affect the analysis, right? To understand this, what we are going to do is we are going to solve this particular problem which contains two elements such as AB and BC whose lengths are one and same 3 meters and EI value and EI value of them are same for each of them. We see that EI is greater than EI in this case, right? And we are applying a point moment or constant moment at this joint B and we are going to carry out the analysis. Overall, what we will do here is we will first consider all three degrees of freedom possible. We know that if we don't ignore axial deformations of these members AB and BC, the kinematic density of this particular frame will be 3, that is UB, PB, and theta B should be taken into consideration. However, if one wants to ignore the axial deformations, then the kinematic density will reduce to 1, which means just this theta B is required to carry out the analysis, right? So what we are going to do is we are going to consider these three degrees of freedom first, and then we'll solve the problem. And later, we'll do the analysis using just theta b as the unknown. I will solve the problem and we'll see how the results differ from one another. Fine. So always it is essential to visualize the deflected profile. Fine. So in this case, what we are doing is we are applying a constant load or constant moment at this joint B. So because of which what happens is this joint will try to undergo a displacement like this. Okay, that means this member BC will try to undergo an elongation in length, whereas this member AB will undergo a compression. Okay, that means this joint will try to move leftwards and upwards apart from undergoing a counterclockwise rotation, right? So in everywhere, what we do is we consider this notation as positive. That is, this direction along x-axis is positive, this direction along y-axis is positive, and we consider counterclockwise rotation moments as positive. Okay, bear this in mind. We will use that later. Now, whenever you draw the reflective profile, one needs to make sure that at every rigid joint, the angle between the members remains same. That's what we see here. Even after deformation, the angle between them remains 90°, right? Because initially the angle between them was 90°. It maintains its, the rigid joint maintains the angle as such. Next, we should see that wherever we come across a fixed support, the tangent drawn at the fixed support should remain intact. I mean, it should remain flat. That's what we see here, right? So these details are enough now. We'll come back to this later, right? Why do we require this is after carrying out the analysis, once we know the values of VB, theta B, and UB, we can relate them to the actual displacement profile and we can justify our answer. We'll do that later, okay? And I'm going to assign a value of 1 for UB, a value of 2 for VB, and a value of 3 for theta B. That helps me in explaining this difference matrix. Okay. So degree of freedom 1 corresponds to UB, degree of freedom 2 corresponds to BB, and degree of freedom 3 corresponds to the rotation theta B. Fine. Going forward, in stiffness method of analysis, what we do is we apply a unit displacement along a particular degree of freedom, okay, arresting other degrees of freedom, and we'll find out what are the member forces or what are the forces generated, okay, to obtain this particular degree of freedom. We do that for each degree of freedom one after the other, and after doing that, what we do is we use them as a linear combination to arrive at the final answer. That means, to explain it better, in this case, see, this is the degree of freedom 1, this is degree of freedom 2, and this is the degree of freedom 3. So first what I will do is I will apply unit displacement along degree of freedom 1, and then I apply unit displacement along degree of freedom 2, and then I apply unit rotation along degree of freedom 3. Okay, and in each case, what I will do is I'll determine what are the forces required to obtain this degree of, or say, displace profile, which corresponds to a degree of freedom, right? And then I will use them as a linear combination, that is UB, VB, and theta B. Okay, the right value will give the actual displace profile. Okay, let me explain it further. First, I'm going to apply unit displacement along degree of freedom 1, right? So I do that, this member will elongate and this member will undergo a displacement something like this. When I do that, you can see that the other degrees of freedom are inactivated, or I would say are inactive, not inactivated, deactivated, or they remain inactive. Okay, so only the translation along this degree of freedom is possible, whereas you see that this joint doesn't displace along y direction, and the members connected to this didn't undergo any rotation as well, because you see that this remains straight, right? That means this member didn't undergo any rotation at this particular joint B. Okay. So first this degree of freedom is imposed and one finds what are the forces generated due to this. We keep them aside. Next we apply a unit displacement along the degree of freedom 2, right? So you see that that's what we do here. Because of this, the member BC will elongate and this member AB will undergo a displacement like this. Now again, you see that the other two degrees of freedom don't come into play. That means, see, you can see that this joint didn't undergo any transition along this direction, and the joint didn't also undergo any rotation. Fine. So for the imposition of this degree of freedom, we will again find what are the forces generated. And the last time what we do is we just impose a unit rotation at this joint B in a counterclockwise fashion, and we will find what are the forces generated due to this, okay, which are in equilibrium. Now, this is what happens if we impose a unit value of each degree of freedom, right? But when we sum up, it need not correspond to, and it would not correspond to the actual displaced profile, okay, for the applied moment at this joint B. Okay, we applied a unit, we apply a concentrated moment which is anticlockwise at joint B. So because of that, this is the displaced profile, right? But for the correct value of UB, theta B, and BB, it will pertain to the actual displaced profile. That means we use these three cases, okay, and we scale up appropriately. Okay, when we do that, for the correct values of UB, VB, and theta B, it should pertain to the displaced profile, right? That's the overall logic. Fine. This is something like, see, if we have a vector here, what we can do is we can use EI, EJ as the basis to get this particular vector, right? So I mean to say, these profiles in which we apply a unit degree of freedom, I mean unit value for each degree of freedom, they serve as a basis. And when you have the correct value of UB, VB, and theta B, it pertains to the correct displaced profile, right? I don't want to uh, say anything further about this. So moving forward, if we apply M displacement along degree of freedom 1, you find what are the forces corresponds to that. Okay. So K11 is the force. So at this joint, what is the force generated in this direction? In this direction, what is the moment generated here? That corresponds to this particular column 1. Next time is when you apply unit displacement along degree of freedom 2, what are the forces again generated? This, and this at this joint is what you see here. Similarly, the third one, right? Now, once you know that, what you can do is you can arrange them column wise like this to get what is called stiffness matrix. Similarly, one gets what is called displacement vector. Okay, in this case, UB, VB, and theta B are the degrees of freedom that comprises the displacement vector, and also what we call load vector, right? In this case, the load applied along x direction at joint B, load applied along y direction along joint B, and then the moment applied along a particular direction at joint B. Okay. So in this case, we can see that I didn't apply any load along x direction or y direction. I am just applying concentrated moment, which is anticlockwise, which means a positive sign should be used. So its magnitude is 25 in this case. So this load vector will look like this 0, 0, and 25, right? Once you know that, in stiffness method, what happens is you get an expression like this: K into U is equal to P, where K is stiffness matrix, U is the displacement vector, P is the load vector. So from which we can get U by inverting this K. Okay. So in order to get this stiffness matrix, what one should do is one should find first what is the stiffness matrix of a frame element. So for a frame element, we know these are the 3 degrees of freedom possible at every joint. Okay, so 3 plus 3 is 6. So the stiffness matrix for a frame element will be of size 6 by 6. We will see later how we get this. As of now, it is sufficient to understand all this. And if you take a particular element out of this, say in this case, this will be K, which row it is. For example, if I take this, this is K, T3. third row, third column, right? So this particular index has a meaning associated with it. That is, if I say any Kij where I corresponds to row and j corresponds to column, Kij is, or I would say Kij should be understood as the force developed along a degree of freedom I due to the displacement imposed along a degree of freedom j. Okay, so that's what. So each of them has a particular meaning in this. So once you know the local stiffness matrix for each element, what one does is one generates what is called global stiffness matrix using this expression. K global is equal to T transpose K into T. Here T is called transformation matrix. Okay, so we'll understand all this later. Once we get the global stiffness matrix for each element, we assemble them. Okay, to get it for, or I would say this is the global, or I should otherwise say the global stiffness matrix for each element. Okay, once you get that for each element, we assemble them to get the global stiffness matrix for the entire structure, right? From which we get a reduced stiffness matrix which pertains to only the active degrees of freedom, and we solve for them. Now I know it is all vague, but later we will understand this when we discuss stiffness method. Okay. So now we know that in this case, these are the 3 degrees of freedom active, right? So this is 3, which means the reduced stiffness matrix should be of size 3 by 3. That's what we see here. See, after carrying out all the process, that is, we need to first define the local stiffness matrix for each element in this case, and we need to use this transformation matrix to convert this local stiffness matrix to global stiffness matrix, and we need to assemble them, and we need to remove the inactive degrees of freedom. Then we arrive at this particular stiffness matrix. Okay. So finally, we write K into U is equal to P, as I told earlier. So in this case, U contains UB, VB, theta B, and P contains 0, 0, 25, right? So now you invert this particular matrix. Fine. One important point is, see here in this case, the degree of freedom is just 3. Imagine for a real structure. For a real structure, it will be 1000 by 1000 or whatever, depending on what is the structure one is handling, right? So inverting this will be very challenging, right? I'll come back to that point later. So here you can invert this matrix, multiply with the load vector, you can get these 3 values. You see that we get a negative value for UB, positive value for UB, and positive value for theta B. I already told that this joint will move leftward, upward, and undergo a counterclockwise rotation. This is consistent with this. That's why I told it's important to visualize the displaced profile, right? See, this negative means that the joint is moving leftward. This positive means the joint is moving upward, and this says that the joint is rotating in the anticlockwise fashion. Right? This is consistent clearly here. So once we know these values, what we can do is one can use the relevant equations to get the values of shear force, bending moment, axial force, and then one draws the bending moment diagram, shear force diagram, and what is called axial force diagram. So just bear these values in mind. We'll come back to them later. Now, if we consider the axial deformations, what we get is 6.2 approximately for the bending moment diagram at the ends, and then again 6.23 for the shear force diagram as well as the bending moment, axial force diagram, right, at the ends. I shouldn't say at the ends. Okay, overall throughout the members, right? Because this is a constant value here. We'll come back to this point later. Now, with this, we are closing the first case, that is considering axial deformation, solving the problem. Now we are ignoring the axial deformation next. That means we are just going to consider the rotation of this joint B as the only unknown. We are going to do the analysis. Now, typically, what one does is one uses the moment distribution method or the slope deflection method, right? So if you consider the slope deflection method, this is the single equation one will get. Okay. So 4EA by L of each member added multiplied by the unknown theta B will be equal to the load 25. The other way in which one can handle this is if one is aware of the moment distribution method, one can easily solve it because EA by L of both of these members is one and same. So you get a distribution factor of 0.5 for each of them, which means if I apply a value of M, MBA and MBC will be m by 2, m by 2. Okay, here I'm applying value of 25, which means MBA will be 12.5, MBC will be 12.5, and the forens will take half of the value. Okay, which means 6.25 and 6.25 should be the foreign moments, that is MCB and MAB. Okay, that's what one gets by slope deflection method as well. From this expression, you get the value of theta B, which is approximately 4.7 into 10 power minus 4 radians. We'll go back to the earlier analysis we did and we'll compare with that. You can see that this is closely equal to the value what we already obtained, right? You can see that, right? These two values are not relevant now, however, but you can see that even when we consider axial deformation, these values are very negligible because 10 to the power minus 6 meters, right? And theta b is closely related, close to the value what we obtained here. Fine. So these are important observations here because you see that UB and theta b are not so significant. Okay, only theta b is relevant as far as the members are flexural. Okay, and then using particular expressions for MB and MAB, you can get those values, right? I already told this will be 12.5 and 6.25 based on understanding using what method? Moment distribution method, right? So 4AB ln theta B and 2AB ln theta B, these are expressions one get using slope deflection method. Once you know these values, that is MBC, MCB, and MBA and MAB, you can draw the minimum diagram straight away, right? And after that, what one can do is one can draw the free body diagrams to get the shear force values and bending shear force and axial force values, right? Earlier I told this value of 6.23 and 6.23, right? For the bending diagram, what we drew earlier when we considered the axial deformations. Now, without considering, we see that it's not much different from what the value we obtained earlier, right? The shape remains anyway same, right? And what about the free body diagram? This is the free body diagram, right, for each of them. That is for member AB, for member BC, and also we require it for joint B because at joint B we are applying a counterclockwise load or moment 25 kilonewton meter, right? So once you draw the free body diagram, you get the axial forces and shear forces for each member, that is AB and BC. Then one can also draw the shear force diagram. But I am not doing that here because it is same as what we obtained earlier. Just the only difference is you can see the magnitudes here 6.25 and 6.25, right? So you can go back there, and earlier we got 6.23. Now we are just getting 6.25. You see that it doesn't make much difference. Just the second decimal is altering. So the basic understanding is, and I also told in the current case where we ignore the axial deformation, we got this value as 6.25. You can see that is 6.2 here when we consider the axial deformations. That means it doesn't differ much once we consider axial deformation and once we don't consider them. Okay. So in this case, just we have 3 degrees of freedom, right? But for a real structure, this degree of freedom will be so high. And then inverting the matrix which corresponds to that will be very, very, very difficult. Okay. So once you ignore the axial deformation, since in a real time case or a practical case, you can see that you can drastically reduce the size of this matrix because invertibility will be a big issue if when the size of this particular matrix grows like anything. That's why it is important to consider axial deformations are ignored and solve the problem. Because in this particular one, we see that the end results doesn't differ, right? I already told that this theta b doesn't differ much, right? And also I told that these diagrams remain one and same, just the second decimal is altering because here we get its value of 6.2 contrasted 6.25 there when I ignore the axial deformations. Similarly, these are contrasted with again a 6.25, value of 6.25. Here we get a value of 6.23. So see that it doesn't differ much. I mean, bending moment diagram, shear force diagram, and axial force diagram they don't differ much when we contrast with the case wherein we ignore the axial deformations, including the rotation. Okay, that's the message I wanted to convey here. Thank you so much for your patient listening. We will meet again in the next video.